There's a third way of visualizing sequences, which is also very natural, and it's very much used in computer science. And, computer science is absolutely superb in this because they really care about allowed sequences or languages or whatever. Curiously, some of the basic ideas in this theory come from Noam Chomsky, from the linguistics or mathematical linguistics. So we can think of the trees as yet another representation of what's possible dynamically. And the way you do this is that you start any place. So let's say we start at A, any place. And then if we have this kind of binary world, we only end up on the bad side or on the good side or left side or whatever. There'll be two possibilities. You can end up in a region. So right now I'll use another way of thinking about what links are. So far the links had to do with going from A to B, but now I'll think a link is someplace where I go to a different world to stay in the same world. Suppose I was starting with 0, or going to a different world, A. And let me call this neighborhoods where I end as B and C. If this puzzles you a little bit, remember we did this for the 3D dynamics. In 3D dynamics we found it very convenient to, instead of keep track of these names of disks, which are totally arbitrary, to use topologically important information, which is that at a bounce I either come back or at a bounce I go to the next disk. And that was what converted this dynamics into full binary dynamics. So you can think about this, I either go to I do what I did before, I do something different. And once I'm there, in general, I have a choice of doing this again. I do the same thing or I do something different. And this goes on. And if you remember, this is what we used to describe spatial ordering for unimodal maps. So this tree we constructed when we looked at the unimodal map, where this whole interval is called 0 or 1, and then we divide it into smaller intervals. 0, 0, 0, 1, 1, 1, 1, 0. And this now we can just obtain by reading, see the yellow line is 0, 0, next to it it's 0, 1. If I go here and turn left, I get region 1, 1, and I get to 1, 0, and this goes on. This tree goes on forever. So it's an alternating binary tree. So this is fine, and this actually reflects the way that in practice we might explore the attainable resolution. We can go down this tree trying to find regions whose future is specified for more and more steps, until we find them too small to keep track of. But the important thing for us is that they were order respective to each other. That was crucial in explaining how pruning happens, how obstruction happens. So if you remember, we found that if a map looked like that, there was a whole region which is pruned. So spatial ordering is very important to us. So this is great, but it's impossible to put on a piece of paper. It just goes on forever. But then you make a very simple observation, which is you realize that when you have gone from A to B, the future looks just the same, because the tree that emanates from this branch is the same as the complete tree. When you go from A to C, if you flip the tree, it looks the same. So from a topological point of view, this is the same. So you can identify A, B, and C, because once you're in any one of these points, the rest of the tree looks the same. So what you can do is, you can say A equals B equals C, and from A I can go to one of these guys in the old-fashioned way, or I can go from one to the other in the different way. In this map, I flipped the neighborhood. And indeed, this is our first example. And you realize when you look at it, you were kind of silly. There was no point of writing this as something with 2 nodes and 4 links. It turns out 1 node and 2 links works just as well. And you'll see this when we start counting trajectories. So both of these things generate all possible itineraries of 0 and 1s, but this is a more compact way of stating them. So one thing that makes the theory of languages or automata difficult is identifying which graphs are actually the same graph, meaning they give you the same admissible sequences. But now, drawing things as a tree, we have a very good connection to pruning, because we know what pruning was. It just meant that there was a part of the state space that stretching and folding was not sufficient to reach. So everything in this region is never reached by iterations of the dynamics. That was what the pruning was. And the simplest example of it is that when the stretching is so weak that it turns out that we cannot end in this whole region. Now this whole region is called 1, 0. We first went the one way, and then we went, 0 is yellow here, and 1 is red or pink or whatever. So this is unreachable, which means that I'm supposed to cross it out. And I can simply erase it. Now I look at the tree a little more carefully, I realize that here I had this sequence that I went from 1 to 0, so I'm supposed to erase it here as well. So what I find is that whenever I start with my 0 symbol or yellow hop, I have 2 possibilities, but if I start with the pink hop, I have only 1 possibility. So it's not true anymore that these 2 guys are the same. B and A are still the same because the future from A looks like the future from B, but B and C are not the same. However, if I go here, here I have the same situation. So let's call this E. So I can identify A and B, and identified C and E, which means that I'll have a node, this node here, which is A equals B node, and I'm allowed to come back. But if I go in the E direction, I'll have to go to C, so I'll have to take my pink jump to C, it goes like that. And from C to C, I can continue, but can never come back. So it turns out if I do some drastic pruning like this one, 1 equals 0, I'll have what I warned you of before, this part of the space. This part of the space will be transient, which means if I start in the neighborhood of this fixed point, which is called 0 to infinity, I'm allowed to jump a few times around. But once I find myself on the right-hand side, I'll be in this region, there are only ones. So this is 1 fixed point. So the 1 fixed point, which is 1 infinitely repeated, is the sink, absorbing, attractive, whatever. So this is a nice example of pruning. If you prune over too zealously, you might actually eliminate any interesting possibilities. So if you're going to prune this, you are not allowed to prune this region. You have to do something a little bit smaller. And if you did something a little bit less bold, which is done in the book as an example, you will find yourself in this golden mean pruning.